Hello again. So I just wanted to explain that we should name that one Z in this case because we're actually finding a solution for our Xi, and that will be Xi X and Xi Y. And yeah, by calculating these solutions, we will actually get like the solution for eta and xi and eta as well. Yeah, that's it. So what we are going to get here is we calculate this, we get x equals s plus a constant 1 and y equals lambda 1s plus a constant 2, and then we will literally get x how can I say, yeah, if you multiply, let's say you multiply lambda 1 x and then subtract minus y, that will give you 0s plus 2 constants, which is another constant. Okay, so you see this here has to be constant, and you also see that if this one, so we had to name it xi, not to that, if that function is 0, that means psi has to be constant as well. So, and if we just name this constant psi, that's 0, if we just name it or just take these values for psi, then we actually have our psi in terms of x and y. So it's all depending on this lambda 1. So in this case, like I told you, I took lambda to be a constant value, but it could be something depending from eta, xi and eta as well. In that case, you will have to integrate this part in terms of s, and it will get a bit more complicated, and you won't get linear dependency of xi and eta. So eta will literally give you the same. If you do the same calculations, you will get lambda 2x minus y. And yeah, if you have non-constant values, these integral will be a bit different, and then you'll get non-constant functions or dependency, or actually non-constant characteristics, because in this case our characteristics will look like this. Characteristic curves in the x y plane, we will have some like functions and some linear functions in the plane. So maybe that's not clear enough. So if you have xy plane, we'll look at all those lines which are constant in the plane, and if you're looking for a solution space and want to kind of project these all the solution on the characteristics to our solution space, which could look like this. We'll get this kind of, I think they don't like it's not clear. I'm not sure if you can see it, but they don't have to be like lines in the space. But yeah, you're just going to expand. Wasn't sure if it's clear to see, but those projections don't have to be constant lines, because you will get another relations, like your solutions will be functions of these coordinates, but not linear functions. So you could get curves in the space. Let me redo that. So yeah, and yeah, basically that's it. If you solve your characteristics, you will get those coordinates in terms of x and y. If your lambda is constant, you will get linear, how can I say, linear dependency from those two coordinates. Actually, yeah, wait, I have to tell you, if these are our coordinates, and we got them from this equation here, these equations actually, from our coefficients, which will be 0, that means if you choose those coordinates in that way, that means that our differential equation, which initially was uxx plus buxy plus cuyy equals first order stuff, will actually be just a new function. That was the reason why we were doing that. Just a new function equals first order stuff. So that means we got rid of those two coefficients, or actually the new coefficients. So maybe I should put in a step. So first of all, we're transforming this equation to a new equation, a hat which is a function dependent from xi x and xi y times xi plus b hat and xi eta. It also depends of those derivation, but I'm not gonna plug them in. Plus, so we have c, we will have c c hat depending from x, y, u eta equals 0. Or we could name it, you could either name it z, as I told you, or we can just name it c, because I don't want to confuse you too much. But normally, because of mathematical rigidity, we'll have to name it z, but it's not necessary in order to get the point. You just can do it, but it's not really necessary for the solution. So let's name it u again. So just that you can see the similarity. It is actually the same function, just depending on depending on the other coordinates, which also depend on x and y. So, and as we saw that this here actually is the same function as a hat, just with other variables plugged in. So this will be the same function, just okay, same as a hat. And we got our solutions for n, for eta x, eta y, psi x, psi y from those zeros, which was lambda 1, lambda 2. In this case, it was a constant one, but it doesn't have to be constant. If it's not constant, we have to consider the integral, and it will be a nonlinear dependency. But at the end, if we take eta and psi from this equation, that means these two coordinates fulfill the zeros of this function. That means these coefficients will cancel out for a specific coordinate system, which we choose to be eta equals lambda 1x minus y, and psi, and eta equals lambda 2x minus y, because these are two constants, and if we now want to solve the equation psi n equals first order stuff, let's say, for example, we always have to solve, just in order to solve this, we always have to solve the homogeneous equation. And what we are going to do is to integrate this function 2 times, and the right hand side as well. But as we don't know the right hand side is really general, we can the solution will depend on the integral of the right side. Yeah, that's the hard thing after doing all the other simplifications. But let's say, let's make another simplification for you so that you could understand the basic problem. So the first simplification was lambda to be constant in order to get linear coordinates or linear dependency of these coordinates, which doesn't have to be the case. Sometimes you will get, or you can get, non-linear dependency in the coordinates like x squared, y squared, and all that, or even logs x, y, and all that. But it's just keep it simple. And for that, I will say that first order stuff will be 0, so we will not have any derivations of first order in this equation. So that's actually the problem, my problem given, and then we can easily simplify this equation like this. We will have to integrate this 2 times. Psi eta. What does that mean? Okay, let me do it step by step. So it's easy. First, we're going to start by integrating it in order of eta, which will get us a function only depending on psi. Why is that? Because look at this form. If that's 0, okay, this means that our function u eta has to be function only of eta. Yeah, so let me rewrite that actually. So we'll get u eta is a function of only of eta. Okay, that's easier. And could also do the same, maybe. Okay, because I started the other way around, maybe it's better to explain it the other way around. So if you do it like this, we will get a function here, u psi only depending of f of psi. Yeah, because if we take the derivative in terms of eta, this will get us 0. This here only can be a function, any function, in terms of psi. Okay, now we're integrating this in terms of psi again, so we get psi eta, and then we will have to integrate this one as well, so we have to find a prime function which is, so let me tell this x f of psi plus a constant, but the constant in this term can also be a constant in terms of yes eta. So we will get this here, this term we can easily name f big F capital F of psi plus capital G of eta, and our function psi eta will equal to this, will be equal to this, and if we want to get it in terms of x and y, we just have to plug in our solutions or our coordinates which we got, which will be this in terms of constant lambdas. Yeah, if you don't have constant lambdas, this will be, so in general this will be a function of, let me name it another function, f hat of lambda 1 x y, and if we keep it general, g hat lambda 1 lambda 2 x y, but that's just the most general case. And yeah, that's it, that's the theory behind this simplification. In the next step I want to show you a example which gives you clear vision of all that, and I think which will enhance understanding and all. So thanks for your attention, and see you in the next video if you're interested. And yeah.